Welcome everybody to the third part of our OptiSystem webinar series. My name is Brian Tipper. I'm the VP of Sales and Marketing here at OptiWave, and I'll be assisting your host, Damien Merrick. In this presentation, we'll be taking a closer look at OptiSystem's advanced features and capabilities. And before we begin, we'll quickly review the webinar basics. During the presentation, we're going to hold two question and answer periods. The first one held approximately 20 minutes in, and the second held at the very end. Please note that we will not be taking questions via the raised hand option, so please type all questions into the questions section only. We'll also pop up 3 polls, such as the one you're looking at now, during the course of the presentation, and if you are in attendance for all 3 polls, you'll be entered into our $50 gift card draw. The winners of each of our draws is announced on our website immediately after the presentation completes. Over in the handout section, you'll find a PDF that's used in this presentation. Feel free to download that at any time. And lastly, this webinar is going to be recorded and distributed to all registrants via an email tomorrow at noon. So again, you're going to get an email tomorrow at noon with the link. Just go ahead and click the link. You may have to enter in your information and hit the register button to get access to the actual video. So just go ahead and do that. If you have any issues with getting the video afterwards, you can always just email us at info@optiwave.com and we'll send the direct link to you. So with all that said, it's now time to get this party started. I'd like to hand over the presentation to your presenter, Senior Photonics Application Engineer, Damien Merrick.
All right, thank you, Brian. Let me just get my screen set up here. Maybe wait for some last people to join in. So today I'll be presenting this webinar on OptiSystem. You've probably seen me in some other webinars this week. We'll be giving Ahmed a break today. He'll be returning later this week to continue on OptiSystem. And we're going to be looking at today some of the more advanced features of OptiSystem. So you've seen the sweeps before. I'll quickly touch on that. And then we'll look at scripting, using parameter scripting, using scripting as a layout tool, laying out the components using a script, doing some data exporting using the script. And then we'll look at another feature called the optimization tool, so we can optimize some parameters according to some results. And then finally, we'll be looking at how to use the Matlab component, and also, that's not included in the title here, the C++ component. And depending on how much time there is, that'll sort of dictate how much time we have to spend on the C++ component. But I'm pretty confident we'll have a pretty good time. Enough time. Next slide. All right. So yeah, sweeps. I've already mentioned all these things. Also, just bear with me this presentation. There's going to be a lot of software popping up. There might be some more delays, more than usual, but I'll do my best to keep it smooth. All right. So starting off with these sweeps. Right, we can choose parameters and sweep them through different values. And I'll show that in OptiSystem. This PowerPoint's more just to lay out the webinar, and I'll be showing pretty much everything in the actual software. It's also a pretty good method to use a sweep to get a rough sort of optimization of a certain parameter, right? So you want to find the sweet spot of something, you can do a pretty quick sweep. It's really easy to set up, and I'll just quickly do that right now. Okay, so let's take a minute here to digest what this window is showing. This is a layout of a modulated laser with a bit sequence. There's an attenuator here that we can control using the attenuation parameter. And there's also the receiver, photodiode, a filter, and the data recovery. This will tell us the BER at the output. Now, obviously, there's going to be some dependence on the quality of the signal with respect to the attenuation we put here. And usually, to find out the quality factor, or rather the receiver sensitivity of a receiver, you say for a certain quality factor, I want to get a certain power level at the receiver. And we can do this using a sweep. So if I go in here to the attenuator, I can change this mode here to sweep. I can go into the box here, and I'll set a total sweep number to 20. And right now, all the attenuations are the same. I can highlight the whole column here, choose linear spread, and I can set the spread to go from 33.5 dB to 39. Okay, and now set up, and it's simple as that. So we would just go to the calculate button. Make sure you choose one of the options up here that is includes a sweep, right? You wouldn't want to choose the calculate current sweep iteration. You want to choose one of these ones up here. And it'll go through all the different sweeps of that parameter. And we'll look at the results in the BER analyzer, which is named here data recovery. So see, for a high value of attenuation, 39 dB, there is a low quality factor. And as we go down attenuation, the BER will be better and the quality factor will be larger. And we can plot this relationship using the report tab. You could click on the 2D graph, click and drag, and then if I have this a little larger here, you can choose the parameters. This monitor is a little bit out of sync with the edge of my screen, but you could choose to display this relationship by first going to the attenuator, find that parameter we swept, attenuation, and drag it down to the independent variable or x-axis. So we have that, and you can see it's increasing. And then we can also plot a result according to that parameter. Go into results of the BER analyzer. We could plot, for example, the let's choose the min log with the BER. And you'll see that as attenuation goes up, the BER gets worse, or it gets larger. You also notice, and it's important to see this, and to mention before, that the BER, it's not a very smooth relationship between that and the attenuation. That's because from a simulation to simulation, some of the effects are random, right? The noise is random, the actual bit sequence is random, so every simulation is going to be a little bit different. However, you can definitely see the general trend here quite clearly. And you can also plot things, two results with respect to each other, so I'll just show that. We could plot the min log BER versus the quality factor to see the relationship between the BER and the quality factor. Let me just find the one I want. And I put the other one on the y-axis by accident. Okay, so here we have the relationship between quality factor and BER. That's just to show that you don't have to, you're not stuck with just displaying things with respect to the parameter. You can do other results, any mix match of any of these parameters on the left and results on the left. Okay, so that was the sweep. You've seen that before. Now let me switch back to the presentation here, talk about scripting. So this phase we'll be talking about scripting. And actually, just before I do this, I'm going to switch to system again and show you this is a phase right before scripting the layout where we're going to talk about how you can use the parameters and script parameters, right? So scripting is a very sort of ingrained feature in all our software, even in FDTD, OptiFDTD, and OptiBPM. A lot of the results and parameters can be scripted right in the software, and I'll show you what that means. So let's say we have a very simple layout here with an optical transmitter in the optical transmitters folder, right? And now let's put a second one down as well. Now you'll notice if you double click on the layout anywhere, you get a list of the current layout parameters, right? So these are all certain values. Here we have this variable called bitrate with assigned value of 10 gigabits per second. If you open up this component, you'll see that it has a parameter called bitrate, and its mode is called script mode. That means that you can type in a variable name here, right? Like we've typed bitrate by default, and this is getting the value from that layout parameter. If I hit evaluate script, it'll show that it's 10 gigabits per second. So that makes it easy if you want to do a simulation with a bunch of different wavelengths, perhaps, but all transmitting at the same bit rate. However, we can also do something where we might want to change this, the second transmitter down here, to a different value of the bit rate. So we could write in here 2 times the bit rate. This is just a simple equation. So now the bit rate's 20 gigabits per second for this component. And if we display that with the visualizer in time domain, we can show quite clearly that the bit rates are different and one is going to be faster than the other. So you could do simulations where the bit rates are related, but maybe you want to increase them sort of uniformly. Like you want to have parameters that are in with relationship to another one, and then you might want to sweep the global bit rate between values. So that's what I would call sort of the scripting of parameters. But you can even do more in-depth scripting, which is the example I'll show here. So let's head back to PowerPoint real quick. So see here, this is the layout I was showing, and this is the associated script with that layout. So it's a Visual Basic script, and the first object that will be available for you to use is a document. And from you call functions on this object to get all the other objects you want to play around with. So you could get the layout and the canvas, and then from the layout and the canvas, you can also get the components that are on the layout. You can create components and place them on the layout, and get parameters as well. And pretty much everything can be manipulated from the Visual Basic script. In addition, you can also start other applications from this visual scripting environment. Right down here, you'll see that I've created an object Excel application, and it's actually going to start that Excel application, and then at the end, it's going to output some results to that table. Also, components can have internal scripts, and I'll return to that feature after this short presentation. This short presentation on the scripting and layout. So before I go into this script, where it's very complicated, you see there's lots of words and functions, I'll show you how you can start off, a really simple way to start off with this type of script without having to write everything by hand. So this is the one I created just before, showing off that bitrate parameter. And from this, you can actually create a script. Right now in the scripting tab, it's empty. If I go to script and say generate, it'll overwrite any script that's there, and then it'll actually write down all the script for you, and then you can go through here, write your own little equations or functions, or see how it actually displays components and creates them. Right here it has the name, the ID. This is all in the manual as well. You'll find all this information. And then the position on the actual layout. So you can start off very easily from this generate script functionality. And then when you have the skeleton, you can start doing more advanced things to your script. And this demonstration is showing, let's say you're modeling something where you have a lot of different channels, right? A lot of wavelengths. And maybe they'll experience different gain through some transmission link, and they also will experience maybe different loss or different dispersion. So they might have different eye diagrams. So let's say you want to calculate that BER with that eye diagram. We do have a component, the WDM analyzer, that does that. But this is also another technique, and you can see how you could use this in other situations to programmatically create this layout. So you see here in the script, there's this variable called number of channels, or num channels, and this is what you could use. I've made this script so that I can set this number to any value, and it'll automatically generate a layout with that many channels, that many wavelength channels. And then before the actual layout is started, the Excel application is started here, and a new workbook is added. And then here we're actually laying out those components, place them in certain positions. And then for the other components, where there's multiple components, we have a loop here. We go from 0 to the number of channels, -1, and we will be creating them in different spots. And then finally, after placing all the layouts, we connect the ports. You have to connect the ports programmatically, and then you simulate. And then here is where it also gets more interesting. We can create these vectors and save the BER result from that BER analyzer, and create another X vector with the frequencies associated with that Y data, and then actually add that data to an Excel worksheet. So I'll show you that first. If I go to Script and Run Script, it'll overwrite the layout. And then, I don't know if it showed up on the webcast there, but we have now an Excel document opened up with the frequencies on the left-hand side and the BERs here. Now you'll notice there's no very real transmission link in between these components. So there's basically no noise or no distortion. So again, the BER is very low, 0. But automatically exported that to this Excel document. And now I could increase the number of channels. If I go here, I could write 15, run the script again. You'll notice there's more channels here and more analyzers. And now this frequency range goes up to 194.5 terahertz, and the BER is on the right-hand side. So that was a simple technique for doing scripting of the layout. And now, right before the poll, I'm going to show a quick example of the components internal scripting I showed on that PowerPoint. So for that, I'm going to have to switch my screens again here, which makes it a little complicated. I had to make sure I had Excel installed. I don't have it installed on my remote desktop. That's why it got a little confusing. So this is an interesting, I think, an interesting application of component script. Right? If you want to have some type of result calculated, we have a lot of default results in our components. Maybe I should explain that first. So here we have, in this layout, we have again another very simple layout. We're just going to be modulating this laser, setting it through an attenuator, detecting it at a photodiode, and then sort of calculating the BER of that system. Now this is an ideal photodiode. I'm starting the simulation here because there's a large number of bits because the BER is very low. So if we want to detect one bit error, we need to make sure we send a lot of bits down using this bit error test set. So as I was saying, you can read the text up here, but basically this simulation is showing quantum sort of shot noise, right? Since the power here is so low, and the attenuator is attenuating quite a bit, there's going to be not a smooth amplitude of the electromagnetic field because the photons are coming in sort of randomly. The average power should be somewhat close to an average value. However, since the photons might not all line up in a row, they might come in at different times, you get what's called shot noise. And this is demonstrating that behavior. That was good timing because the simulation is just about finished. You'll notice we sent in almost 1 million bits here and only got 9 bit errors. So as you can see, it was a very, very low bit error rate system. It ran the other layouts. I only wanted to run the first one. I should have checked that properly. However, we got what we wanted. So I just want to show that after this optical attenuator, part of this sort of application here is to look at the power and how that relates to the noise. And if you right-click and go to component results, you'll see there's a lot of default results that are calculated at each analyzer. And in some components models, they also have results. So here, for example, we have the total power, the signal power, and different polarizations. And then here we have this user-defined one called the average photons per bit. So you can add your own results here. If you click Add, you can write in a result name, and then you can give it a value by using that component internal script. So if I look at this, go to the component script, you'll see that using the bit rate and the total photons that's been gathered by this power detector, which is an already stored result, you can calculate the average photons per bit, right? So you can calculate your own little results here to display that will automatically be calculated for you. And this is used because there's a relationship between the average photons per bit and the BER you should expect if you only have shot noise with your system. So here we have about 6 photons per bit, and the BER is around, it's on the order at least of this BER here. It's 8.5 or 8.6, whereas theory calculates it should be around 3 times 10 to the negative 6. But that is the randomness expressing itself. Okay, so at this point I think it's a good time to have that quick poll passed off to Brian. Any questions, please ask them in the question box, and I'll read them while the poll's going on. So please take it away, Brian.
Okay, so we have the second poll up, and while you're answering that, please also keep in mind that we have 2 additional OptiSystem webinars coming up tomorrow and on Friday. And just looking at the schedule quickly, the session tomorrow is at 9 a.m. It's going to be on advanced applications, and the session on Friday is going to be a second series on advanced applications, also at 9 a.m. Eastern Standard Time. So if you haven't yet registered for those, please go ahead and do that. And for any other inquiries that you guys might have, you can send them to, if it's related to evaluations, or maybe you'd like the software quoted, you can send an email to info@optiwave.com. Or afterwards, if you have a specific technical question that you didn't think of, or maybe it's a little more in depth that you wanted to ask privately, you can send an email to support@optiwave.com, and we'll go ahead and get back to you with all that stuff. So I'm going to give it another 10 seconds or so for you guys to get your questions down and Damien to have a chance to read through them. And then I'm going to go ahead and close this poll. And I think right about now it should have been enough time for you guys to get those questions in. So I'll go ahead and pass it back to Damien.
All right, thanks. Doesn't look like there's too many questions, and the ones that there are, I think I can answer them more directly. So we'll continue on with the presentation, but remember there's always going to be a Q&A period at the end of the presentation. You might have more questions when we go through the Matlab and the C++ component, so feel free to ask them at that time. So moving back to the presentation here. I'll talk about optimizing the parameters. So the parameter sweeps where you change the parameters sort of manually by using your own values, and the optimization is sort of similar to that. However, you tell the simulator that you want to target some value. Maybe you want to maximize something, or you want to get it to some result, and then the simulator will automatically choose the next value of that parameter you want to modify to get as close as possible to that value. So it's optimizing a parameter with respect to some result that you're going to designate. So I'll show this another quick example. I'll let you have some time to digest this image here. So we have some signal here, a continuous wave laser, which is modeling the signal. It's being coupled with a pump, this pump laser down here. They're both be traveling through an erbium-doped fiber, which will provide gain to the signal, and then detected at this WDM analyzer. And the idea here is that we want to choose the proper length of erbium-doped fiber that will result in the best gain of this continuous wave laser. Right? If the length is too short, then that means that the signal propagating through it won't have enough distance to maximize its gain, and if it's too long, then the pump laser won't have enough power to have a complete population inversion over that whole length of that fiber, and you'll get some attenuation, and the gain will drop off with respect to length. Okay. So what I'm going to do here is I'm going to go to Tools and Optimizations, and I'm going to choose a single parameter optimization because we want to do one parameter, the length, and one result, which is the gain. So here we'll see, first thing we want to do is we want to maximize type. So we want to maximize this result. And we're going to move our tolerance down a little bit. So we want to have it to narrow down the best length to within 0.2 meters. Now, as I said, in the parameter, we're going to want to change that length of the erbium dope fiber. So I've added it here. And now we can choose a minimum and maximum value. So we'll stick with 2 for the minimum, and we have a maximum, we'll put around 25. And now we choose a result we want to maximize, which will be within that dual port WDM analyzer, and it's the gain right at the bottom here. We'll add that. And since we're maximizing, we don't have a target value, that's as much as you have to do. Hit OK. You'll see it's loaded here in the optimizations, and we can hit OK. You also notice that now this length is in optimize mode. If you go to calculate, we can run this optimization. The first thing you have to make sure you do is just click this run all optimizations checkbox to make sure it actually runs the optimization. And then you can hit the calculate button, and it will give you a plot over here of how it's converging to that final gain. So it's modifying that length each simulation and then trying to zero in on a gain that's maximized. So we see here now that we've maximized this gain for a length of 5.514 meters, and it was pretty much a success. So that I want to show how easy it is to set up optimization. Obviously, you can't always blindly just set these parameters. You have to do some investigation or figure it out through theory. However, the optimization can take you that final step of the way and get a very accurate answer pretty quickly. Okay, so that's what I wanted to show for optimization. Now we're going to move into the more meaty stuff. First, we're going to talk about how to use the Matlab component to pass data back and forth between system and Matlab. So let's open up a blank file here. I'll just close this one. Don't need to save it. Okay. So I think the first step to learn something is learn the basics. And we're going to send a binary sequence into the Matlab component and then capture it at the output to make sure we're doing this interface correctly. So we're going to send in a random bit sequence, and we're going to choose the Matlab component, which is in External Software Tools, Matlab component. And now, as Ahmed showed you in the other webinars, we have different signal types. So we have a electrical, optical, and binary, or M-ary. And we want to do a binary type port because we're going to sending in a binary data signal. And the output, we also want to have binary. So we have to change the properties of this Matlab component to accept binary data structures. Now we can connect it up, and it'll, before it wouldn't have allowed us to connect that up, but now it will. And we can put a binary sequence visualizer on both ends of this simulation to detect if we actually successfully did this. Okay, so heading back into the Matlab component, you'll see that this is the command it's going to run. This is the first thing, once the data structures are created by system and passed to the Matlab workspace, this is the command it's going to run. It's going to say output port 1 equals input port 1. So this is copying all the information at the input port and then saving it in a new variable called output port 1, which OptiSystem expects you to have properly formatted for the output. So I should be able to run this. And now at this stage, it has to actually load Matlab. You'll see in the taskbar that opened up there, run the Matlab code, and then send the information back. So that was just to show how to run, get the interface set up. But usually you don't want to run such a simple simulation. You want to be able to write some code in a file, an M file, a Matlab file, and then run that. So what we can do here is we can call, instead of calling an actual command, we can call a script, a Matlab script. So let's create a file called test that I will create now, and we'll call that text file. I'm going to put it on my desktop. Over here, we'll make a new text file. And I'm going to write in it the same command, output port 1 is equal to input port 1, semicolon. And I'm going to save this as an M file on the desktop. And I'll call it test, the same command we called in the Matlab component, .m. And I'll delete this one here that doesn't have anything in it. So now if I set this up properly, it'll call that test MATLAB file and execute whatever MATLAB commands are within that file. One thing I have to do, though, is I have to include the search path of this MATLAB file in the MATLAB search directory. So you see here, MATLAB search path. I'm not always sure whether the desktop's included in the default search path of MATLAB, but I'll add it explicitly here. So I can, one trick is to right-click on the file and then copy this path. If you shift right-click, you can do this quite fast. And then paste it in here. Just remove the extra things besides the directory. And then we should be able to run this, and then instead of running the command, it'll open up this file and then run the command within that file. So here it's opening up MATLAB. Apparently I wrote capital T in here when I should have wrote a small or lowercase t. So we'll try it again. And here we have it working properly. So the interface is better now, and now we can actually write code in here to do what we want. But first, let's see what these data structures actually look like. And the best way to do that, you can read our documentation on it if you want, but I think that it's better to actually open up the MATLAB workspace and see what's going on, because I always forget myself. So if you go in the MATLAB component here and you hit load MATLAB, this will actually open up the MATLAB application command window and keep it open. So it doesn't open and close. Now it'll just stay open. If we run it, it'll keep this window open here. This is the MATLAB command window, so we can write any command we want in here. For example, you can write workspace, and this will open up the variables that are existing in this current workspace. We have input port 1 here and output port 1 as well. So let's open up input port 1 just to see what it looks like. We can see that it's got the type of binary, which is some string. It's got a variable called bitrate, which is a double value. It also has another data structure in here, which is a matrix or a vector of binary values. So this is the actual binary sequence. It goes 0, 0, 0, 0, 0, 1, 0, 1, right? And it's completely random. And since we copied the exact structure of that input port, it's going to be saved in the output port as well, in exactly the same way. However, now if we modify this, it'll send a new signal out to the output port. So let's try that. I'm going to program live here, and it always makes me a bit nervous to do this, but I'm going to try and just do a simple modulo 2 of that sequence. So right, that bit sequence was saved as that variable called sequence, so we access it by using the point operator, decimal operator. So output port 1 dot sequence is going to be equal to the old sequence. It's case sensitive, as we just learned. Plus, we're going to add 1 to all the bits. So it's going to be a vector with the first dimension of 1, and the other one is going to be the length of the output port 1 dot sequence. And let's hopefully I got all these parentheses matched up here. And then if we want to keep it as a binary sequence, we need to do the modular too. So we want to change all the ones and zeros and all the zeros to ones. This is one technique to do that. I think it's very simple. So here we're going to access that same variable, and it's going to be equal to, we're going to call the mod function from MATLAB's library, and we're going to act on the output port 1.sequence, and we're going to modulate it by 2. So this is the new function that's going to be called in this. I just want to make sure I have everything correct here. I think I do. So I'll save it, and now I can run this again, and we should see it create the sort of opposite binary sequence at the output. We can compare. So yes, it did seem to work. We have, see, here's a big gap in the output, and then the input's the reverse. It's a 1. So it's about as simple as that to use the MATLAB component. Now you can just get into the MATLAB code, and that's basically just an exercise in knowing the MATLAB language. The interfacing, I think, is the most difficult for beginners to get their head around. But using that workspace command and looking how those variables work makes it pretty easy to debug and to work on your project. There are certain things that you have to take care of. You have to make sure that you match the number of the size of the sequences, right? I couldn't add extra bits to that bit sequence because then the system might be confused of how that's being interpreted. And also the same goes for the optical and electrical signals, where you can't just add more data to that signal. You have to actually only modify or at least make it usable by the OptiSystem framework. Okay, and I can show a more interesting example of MATLAB. For example, we have one here that's amplitude modulator, and I'll run it while I talk about it. So here we have two different optical signals being muxed together and then being sent through this MATLAB component, which is being modulated by this bit sequence. So at one frequency we get this nice optical time domain value, which is being switched by this bit sequence generator, and we should be able to see the two peaks, the two different frequencies that are being muxed together, being sent through this MATLAB component. And there's other examples as well. One example is we can call, let me just close OptiSystem. We can call system from MATLAB. So open up MATLAB using the MATLAB code. It's going to be very similar to the code I did in the VB script. A little bit different, but also very similar. So here it's going to be starting the application, OptiSystem application, waiting for it to start. That's what this loop is for. And then it gets into activating the layout and starting to modify the layout. And it's going to calculate the simulation and then also save the gain, the noise figure, and the optical SNR in vectors and display that in a figure. So let's run that and see how it works. So you didn't even see OptiSystem start up there because it quits at the end. But we get these plots of gain, noise figure, and the optical SNR. So you can, the same way you can use VB script to call OptiSystem, you can also use the MATLAB to call it. I'll just show the project layout if you're interested. Here, right? It's just a continuous wave laser and EDFA, and then there's a WDM analyzer here where we're getting those results from in the MATLAB code. Okay, so to rehash that, the data is pasted as data structures into the MATLAB component, and it must be also passed back as the same data structures in the output port. And the shape, not the shape, but the structure of this the data has to match what OptiSystem expects. You can't make up your own. You have to copy the input. If it's optical, electrical, or binary or M-array, you have to copy that and then make it the same for the output. So that's great. MATLAB is great, but you saw that when I had to run that MATLAB code, it had to open up MATLAB, and there was some slowdown, right? It had to open up MATLAB, then it had to execute the MATLAB code, and then close MATLAB, and that took up some time of the simulation. Also, you have to have a license of MATLAB to run, so that costs money. So those are some downsides of Matlab component. So to address those issues, we now have the C++ component. So you can compile C++ code into a DLL, and in this, I'll show you the project file. We have a solution file that automatically does all the extra things you have to do to make this DLL work. We also include our OptiSystem libraries, like our how to transform the optical signal to time domain or frequency domain, and we also have some mode solving, some fiber mode solving functions available. And since the C++ interface is a little more complicated, right? You have to know C++ because you'll be programming in C++. However, it executes very fast, and it's free because you can download Visual Studio Community 2013 for free from the Microsoft website, and there's a link on our website to that download link. And you'll see once I open up this project file, it might be fairly complicated. However, there's only one function you actually need to edit, and I'll show that right here. So I'm going to my C++ example folder, and I'll open up this solution file. Right, so the only one you have to worry about is the one that's found in the source file DS System Manager in CPP co-simulation project. And the function is calculate API. So you type all your code in here that you want to do. So the first thing you do is call some functions, initialize globals. You'll have this file as well, so you can start off from the starting point to create your C++ component. And this one you'll see what it does is it gets a pointer to that input port that's sending information into the C++ component, and it's looking for a binary signal. And then it's doing the same thing we did in the Matlab example. It's going to do the modulo 2 of that binary signal. When it's done that, it's going to get the signal from the output port, or the location and memory of that output port, and then assign that pointer the signal that we calculated from this function up here. And then we just close off some if statements in case there are any errors, and then return 1 for successful. So you would build this in x64 under release. And once it's succeeded, you'll find that in the x64 folder under release, there should be a DLL here called cpp co-simulation.dll. So if I open OptiSystem now, start a new project, I will again put in a bit. The binary sequences are the easiest to use. That's why I'm always showing them. And I'm going to go into the external software tools under the co-simulation library, and that's where you find the C++ component. And now, like the Matlab component, we have to change the inputs to what we expect. We're expecting a binary, and the output's going to be binary as well. The final step is to send that location of that C++ file to the component so we can browse there. I put it in this C++ folder under working copy, and then you remember I located it in the x64 release, and there it is. And now I can connect up my ports and put some binary visualizers just to see what we're looking at here, and then run the simulation. And you'll see how fast that was. It's native speed, right? So there's no intermediate step where you have to wait for OptiSystem to open up Matlab and do that. And we should see here that we have the modulo 2, or the opposite of that input binary sequence here. We've got a low value, and the output we have a high value. And that's how you would use the C++ component to get your first interface going. So that is about as much time as I have for the presentation. And I'll just remark on some last things here before we do that final poll and answer some questions that you have that I see here in the questions box. So again, you saw it was a little more complicated to set up that C++ component, but we have a lot of web material at that link shown right now. Or you can just do a Google search with OptiWave and C++ component, and you'll find it there as well. So we have PDFs explaining how to set it up, links to tutorials, and also some of the default project files that you can use. So if you want to learn more, it's just best to get started there and download and start trying it out. The only thing extra you'll need is that Visual Studio Community 2013. It has to be the 2013 version. On a future note, another feature we're going to be adding to OptiSystem is the ability to do Python scripting. That's coming in OptiSystem 15 in a couple months. And you'll be able to do the same thing as Matlab, right? You'll be able to write a component and use Python to do the calculations in your Python component, as well as you'll be able to use that Python language to script the layout of the OptiSystem project. So, for example, how I use the Visual Basic script to create different components and connect them, and in Matlab I did something similar. You can do that with the new Python scripting that'll be available. And of course, Python's free and a very, very largely used language in scientific computing. So there's lots of libraries and things you can use for free from there. So I think that'll be a very good source for users in the future. However, one thing, it might be slightly slower than the C++ component because it's an interpreted language. Okay, so thanks for listening to this webinar. I'll pass it off to Brian here as he makes some closing comments, and I'll look at some of the questions you've asked here in the meantime.
Okay, so last poll's up, everybody. Please go ahead and answer that. Greatly appreciated. There are quite a few questions that are coming in, and some of them are fairly lengthy, so I'll try to delay the as much as I can to give Damien a chance to read through them. And just to let you guys know, there have been a lot of you that have attended all the OptiSystem sessions to this point. So the next two on Thursday and Friday are going to be on advanced applications. So if that's what you've been waiting for the entire time, then you'll get what you want tomorrow, and we'll dig in deeper into the guts of the tool and actually look at things that are applicable in the academic corporate worlds, and just investigate how to put those designs together and analyze them. So with that said, the links I put all in the chat for you guys. If I'm not sure if you've had your chat open the entire time, but you'll see the link to the web page where you can sign up for those other sessions. Also, we'll have the winner of the draw announced in about 10 minutes from now. And all the previously recorded webinars, you should have been receiving emails this entire time for anything that you've already attended or registered for. If you haven't, you can always visit that page where you signed up, so the one that's in the chat window, and simply just click on the webinar. It'll look like you're re-registering for it. I'm not sure, this is just how GoToWebinar sets it up. Just put your name in the way that you did when you registered, click the register button, and it basically just kicks you right to the video recording. Okay, with all that said, I'll go ahead and close the poll and hand it back to Damien.
Thanks, Brian. So I see there's some questions here, and that's pretty exciting because a lot of them are actually about the Matlab component. However, some of them are pretty specific questions that I probably will be hard to answer verbally over this webinar. Some are asking, how do you do specific modulation formats in a Matlab component? And that's just a question of learning Matlab, right? If you just need to learn how to do that in Matlab, and I can try and help you out in the forum. If you post your question to the forum, you might be able to get some help from us there. But yeah, some of these questions are like research projects, so you might want to spend some time to learn how to do it. You might have to spend just some time to learn how to do it and just program it in MATLAB. There's another question here about what kind of limit is there on the number of C++ and MATLAB components and number of ports on these components, and that's a good question. I don't think there's any hard limit. I'm not aware of any hard limit. There's definitely examples we have of, of multiple MATLAB components and multiple C++ components. However, I'm sure if you start adding thousands or hundreds of thousands of components, there's going to be some issues. But there should be no sort of reasonable limit on how many components you can put in. Again, the MATLAB components, the more you have, the slower it's going to be, right? Because that's to constantly open up and close MATLAB application, which takes some time. C++ though should be very quick and very fast after you compile it and run it. Okay, so that sort of concludes the questions that I can answer verbally over here on the webinar. I'll get back to some of the questions over email. So thanks for listening to this webinar. Hopefully you learned some of the basics of how to connect some of the more advanced features to your own layouts and learning how to use them properly. And I'll hand it back to Brian here if he has any last words for you. Thanks a lot.
Okay. I think that's a good wrap, Damien. Thank you very much, and thanks to everybody that joined. Have a good day, guys.